Namaste. Welcome to this channel, Dr.ARM's Chemistry. We were discussing the chemistry of transition elements. Under this topic, we have seen many introductory points, and today we are going to see the next point in the coordination chemistry of these transition elements, and this is the coordination number and geometries of complexes of transition elements. Here, these elements of transition series, that is 3D, 4D, 5D, etc., they can give their variety of complexes depending upon their coordination number. And we have seen that the coordination number depends upon various factors such as size of the metal ion, size of the ligand, charge on the metal ion, as well as the bulkiness of ligands. And there are many other examples which can show that the coordination number is not as per expectation. This is because of the repulsion or bulkiness of the ligands. So we will see what are the facts here. So the title of this topic means point is coordination numbers. Coordination numbers in solid state. So we will see the outline systematically when the occurrence of different coordination number is seen. The geometries in the solid state of the D block elements are also discussed here. So first of all, we will see there are some examples in which the coordination number is found to be misleading. So first point, we see that misleading coordination numbers. Misleading coordination numbers. For example, alpha, we can see here PdCl2. Alpha PdCl2. So here we can expect that the coordination number of this PD should be 2, but this is not so. Now if we see the structure of this polymer, so this is a polymer, and we can have the structure of these polymers like this. Like this. So here you will find that the coordination number of this polymer, means palladium, in this complex is 4, but it appears to be 2 here in the formulae. So there are some examples which can be seen in this way, which are misleading. Now we will see that sometimes the bonding mode is to be considered while discussing the formula. So, your second point is to be remembered as bonding mode of the complex. We can see that there are some examples in which you will find that, for example, so here you will find that the bonding mode here is different, and we can see another example. So here you will find that the structure of this complex the bonding will show that this titanium is bonded to these atoms. So this is 1, 2, 3, 4 and 5. Similarly 1, 2, 3, 4 and 5. So this is the structure of this complex. Here eta 5 indicates that this titanium metal is attached to or bonded to this ligand using the 5 atoms or 5 points of attachments, and that is why it is shown as eta 5. So similarly here you will find that this C5H5 is also having 5 points of attachments with this titanium. Again, if we are having this, now it means here eta is equal to 5, and now if we see another example where eta is equal to 1, C5H5 twice Cl2. So here you will find that eta is equal to 1, and the structure is like this. So here you will find that eta means this is called a heptacity. Eta indicates heptacity, means how many points are there in ligands which can be coordinated with metal ions. So here we will find that this metal ion is coordinated with this ligand with only 1 point of attachment, that is this point. But here you will find that the titanium is attached with 5 points of attachment with each ligand, that is C5H5N. So this is called this bonding mode, and this is called heptacity. So these are some basic important points which are used to study or discuss the complexes. Now we will see the complexes with varying coordination number and their geometries. So first of all, we will see the complexes with coordination number 1. Complexes with coordination number 1. For example, we can have this example, that is tellurium 26 trip 2 to C6H3. C6H3. Another example is in iron indium, same 26 trip twice C6H3. Here the coordination number 1 is very rare, and it is arising when the ligands are highly bulky. Here this ligand 3 is here 246 try 246 isopropyl. Iso we will shortly represent as only I, that is isopropyl, that is 246 try isopropyl C6H3. C6H3. Such type of examples are rarely found, and these are the 2 examples. Now we will see how is this structure. So for example, it would take this is a metal, that is M. You can have any, or it will take specific example of this iron. Now this iron is bonded with like this. Then this is further attached with So this is the structure of one of this. So we can replace this indium with Tl, that is thallium. So you will get this geometry is very rare, and this group There is only one point of coordination. This metal is attached to here. With this, using only one point of attachment, and this remaining structure is of the ligand, which is shown here as like this. So here this DrP is nothing but this 2, 4, 6. So for example, if it is started from here 1, 2, 3, 4, 5, 6, 2, 4, 6, triisopropyl. So in this way, we can explain the coordination number and geometry. Now we will see another coordination number. It is coordination number 2. This coordination number is also rare. It is most commonly observed in case of D elements when the configuration is about, or it is most of the times D10. When the configuration is D3 or sometimes D5 as it is observed in NN. There are several examples of this configuration of D10. There you will find that AU, HG or CU, copper. Then we can have these examples. AG is also there, AG. So these matrices can give the complexes with coordination number 2. Here the simple complexes found are like this. For example, we can have this AgNH3 twice plus 1, AgNH3 twice plus 1. So this has a linear structure like this. So this is linear geometry of this complex. So in this way, when the coordination number is 2, the complexes are exhibiting linear structure. So we can have the various examples of these structures like this. If we take this silver, we can have this example. Similarly, if we take copper, the example is CuCl2 minus CuCl2 minus. Then if you take this gold, it has AuCN2 minus AuCN2 minus. Then also we can have variety of examples such as AU PR3 twice plus then we can have another example R3P AuCl R3P AuCl. If we take Hg, the example is HgCN2. HgCN2. So there are a variety of examples. So we have seen the example of Ag as AgNH3 twice plus. Then we can have another example Mn. Here the configuration is D5 as we have seen here. So we will have this example Mn NSi Me pH2 twice. So this example of Mn shows that it is expected they in higher coordination number, but because of such a bulkiness, very high bulkiness due to this methylphenylsilyl or silyl-methylphenyl group and amine, it is amine. So there are such two ligands which are having this very large bulky group. So here NSi Me is methyl group, pH phenyl. So there are such two groups attached to this Mn. So because of this bulkiness, that is bulky amido groups, amido ligands are associated with coordination numbers which are lower. Here we are expecting the higher coordination number of these species. So this is about 2 coordination numbers at time. Now the coordination number third coordination number is 3. This is generally gives the geometry to the complex which is expected to be the trigonal planar. So geometry expected here is geometry. Expected here is trigonal planar. When the ligands are very simple and identical and smaller in size. But when the ligands are bulky or of different nature, then the geometry, trigonal planar geometry, is found to be somewhat lying closer to trigonal planar. Means it is distorted to some degree. For example, we can consider this structure. This has charge plus 1. So this structure is usually trigonal planar, but if the ligands are of different nature, then you will find different distorted structures. We will show some other examples. For example, AU, that is gold, PPH3 thrice plus. That another example is CuCl3 2 minus, then Au PPH2 PPH3 twice Cl, then Ag PPH3 thrice plus 1, then HgI3 minus, then HgS PH3 thrice minus, then PT PPH3 thrice, and another example is PT Bu to H Bu to H thrice. There are other examples. MnO3 plus, then CuS Me3 thrice, Me3 Cl Na3 Cl. So these are some of the coordination numbers we have discussed today. So we have to remember that the geometry of these complexes are governed by various factors such as size of the ligand, size of the metal ion charge on their ligand, bulkiness of the ligands, etc. Hence electronic effects are observed here on these geometry of ligands. So we will stop our discussion here. Please subscribe to this channel, press bell icon and like button also. Thank you very much for watching this video.